this section, we are going to talk about the matrix of a linear transformation. Up to now, we know that if L is a linear transformation from Rn into Rm, then there's a matrix A that does the job of L. That is, L of x, and x is any vector in Rn, is equal to this special matrix times that vector x. We're going to update this. If L is a linear transformation from a finite dimensional vector space V into a finite dimensional vector space W, and in dimension of V is not 0, and in dimension of W is not 0, that is, they have more than just a 0 vector, then there's a matrix. L of x is the same as A times x, no matter what x you pick from V. So a matrix exists for any linear transformation. No matter what the linear transformation is, you could find in A such that L of x is equal to A times x for any vector x. And now, let's state this theorem. It's going to seem complicated, fair enough, but we'll get through it. Let L be a mapping from V to W, which is a linear transformation. Let the mapping L from V to W be a linear transformation of an n-dimensional vector space V, and n is not 0, into an m-dimensional vector space W, and m is not 0. Okay. Further, let S equal V1 up to, I guess, Vn, because V is n-dimensional. Let this set S be a basis for V. And T equals to W1 all the way down to Wm be a basis for W. And since W is m-dimensional, m-dimensional vector space W, T being a basis for W has m elements. So far, all I did was state a basis for V and a basis for W. The basis for V, I'm calling the set S, and the basis for W, calling the set T. Put a line here, but the theorem still continues. So, this here was one chunk, and all it said was that S and T are bases for V and W respectively. Now it says, then the M by N matrix A, whose jth column, so I'm describing the jth column of A, whose jth column is the coordinate vector L of Vj, okay, let me state it, with respect to the basis T. Now, if you think about it, Vj comes from S. So, we find the coordinates of every vector in S with respect to the other basis T. So, when we write A, the first column is going to be L of V1, to be exact, the coordinates of L of V1 with respect to T. That will be the first column. And the second column of A will be not L of V2, but the coordinates of L of V2 with respect to T, all the way down to L of Vn, the coordinates of that with respect to T. So these are the columns of A. And that's exactly what it said. The last two lines, that's exactly what it stated. Okay. So the coordinate vector L of Vj with respect to T of L of Vj with respect to T. And this matrix, the M by N matrix A, whose J's columns happen to be defined this way, is associated with L and has the following properties. Okay. I obviously ran out of space, so I'm going to have to put the properties on the top. So all I'm erasing is that L is a mapping from V to W, the linear transformation, the dimension of V is N, the dimension of W is M. Matrix A has the following properties. If little x is in V, then L of little x, the coordinates of that with respect to T, is going to equal to the matrix A times the vector x, the coordinates of vector x with respect to basis S. And L of x with the coordinates of that with respect to t. You know, I want to write down something. I said it, but I didn't write it down. Where x in brackets of S is the coordinates of x with respect to the basis S. Now, okay. I want to say also this matrix A is unique. And of course it's unique because the columns are the coordinates of L of, or their J's column is the coordinates of L of Vj with respect to basis t. And the coordinate vectors are unique with respect to a given basis. So the next thing we're going to do is we're going to talk about how we make this matrix A. And we're going to do this by working out a problem. I'll give you a linear transformation. I'll give you two bases. Let L be the mapping from R3 to R2. Let L, the mapping from R3 to R2, be a linear transformation defined by the following. L of x, y, z is y minus z and x plus y. Further, let S equal to V1, which is say 1, 0, 0. V sub 2, which is 0, 1, 0. V sub 3, which is 0, 0, 1. So S is a basis, and it's a natural basis. Okay, let S be that, and T equal the following. W1, which is 1, 0, and W2, which is 0, 1. And T is the basis for R2, the natural basis. So let's formally say this. Let S and T be bases for R3 and R2 respectively. And we want to find a matrix A. Find the matrix A. The first thing we want to do is find L of all the vectors in R3. L of 1, 0, 0 is equal to, well, how do you get the first component? You do the second minus the third. 0 minus 0 is 0. How do you get the second component in R2? You add the first two entries, x and y. In our case, 1 and 0. So we get 0, 1. And now we want to write this as a linear combination of these vectors. Okay, I'm just going to change my notation. I just realized I've been writing the vectors horizontally. Well, okay, so little typo. Use a different color. Over here, by the definition, I wrote the vectors vertically. I guess to save space, or actually I didn't realize it. I should have written V1 that way. I should write V2 that way. And V3 should be vertically as well. Okay, it's just notation. Okay, so let's keep it that way. So L of V1, 1, 0, 0, we discovered that was 0, 1. And likewise, let's write these vertically. 0 and then 1. Okay, so now I want to write this vector in terms of basis t. That is some scale of 1, 0 plus some multiple or scalar of 0, 1. And since this is 0, 1, I'm going to take 1, 0, 1 and 0, 1, 0. So this tells me that L of 1, 0, 0, the coordinates of that with respect to the basis t is 0, 1. 0, 1. Now I take L of the second vector in S, which is 0, 1, 0. I do the second minus the third. 1 minus 0 is 0. And then I do the first plus the second, x plus y. 0 plus 1 is 1. I get 1, 1. Okay? But I want to write this in terms of basis t. I want it to be a multiple of 1, 0 plus a multiple of 0, 1. Well, if you notice, if you add these two vectors, 1, 0 plus 0, 1, you get 1, 1. So I really want 1 times 1, 0, which is 1, 0, plus 1 times 0, 1, which is 0, 1. And if you add them, you really do get 1, 1. So that tells me that the coordinates of L of 0, 1, 0 with respect to the basis t is 1, 1. Now I take L of the next vector in S, 0, 0, 1. And what I get is first I do 0 minus 1. I get negative 1. And then I do 0 plus 0, which is 0. And I want to write this as a linear combination of the vectors in T. So it's some scale of 1, 0 plus some scale of 0, 1. Well, I hope you see it. If I multiply the 1, 0 by negative 1, I get negative 1, 0, meaning I don't have to add any of the vectors 0, 1. That tells me that L of 0, 0, 1, actually the coordinates of L of 0, 0, 1 with respect to the basis t is negative 1, 0. Now I make up the matrix that has those vectors as the columns. So I'm going to remove most of this. The matrix A just has those three vectors in the same order as its columns. Matrix A is 0, 1, 1, 1, negative 1, 0. This was the first column, this was the second column, this was the third column. Because this 0, 1 was the coordinates of L of V1 with respect to the basis t. And 1, 1 was the coordinates of L of V2 with respect to t, and then L of V sub 3, the coordinates of that with respect to t. Okay. Let us see if this works. Let us see if this works. Maybe we made a mistake. Suppose we take this matrix A and we multiply it by x, y, z. And we want to get y minus z, x plus y. If you dot the first row with x, y, z, you get y minus z. Work it out, make sure. If you dot the second row, what's the one and only column we have? You get x plus y, which is exactly what we wanted. This is 8 times big X. And it turns out that it was exactly L of X. It's exactly L of X. A times the vector X gave me this answer. But that's the same as L of X. L of capital X. So it's pretty neat how we can find the matrix. Now, one of the things you need to do is go home, you probably are home, and sit down and memorize the steps. If you want to find a matrix associated with a linear transformation, you take, so if you want to find a matrix associated with the linear transformation from V to W, find L of each vector in V and find the, so you need a basis, S, and you need a basis T. So I didn't mean to say you find L of every vector in V. That wasn't true, sorry. You find L of every vector in S, and you write it as, you write the coordinates of L of each and every vector in S with respect to the basis T. And that's going, whatever this equals, that's going to be the columns of A. For each V that's in S. V1, this will be column 1 of S, of A. V2, Whatever you get here, that will be the second column of A. V22, the coordinates of L of V22 with respect to the basis T, that would be the 22nd column of A. Again, in my opinion, you need to be able to say this. Okay. Let's do this problem all over again, except we're going to have a different basis S and T. Okay, we're going to define L of x, y, z to be the same answer. Well, I guess I'm reversing these. X plus y and y minus z. So L goes from R3 to R2, into R2. But here, we're going to have a different basis. We're going to have 1, 0, 1, call that V1, and then 0, 1, 1, call that vector V2, and then 1, 1, 1, call that vector V3. And that's our basis for V. Let me state it. L to the linear transformation from V to W. Now, the basis for W and it turns out in our case that V is R3. I should just say equal. And W is R2. Goes from V3 into W2. It might not be onto. You might not hit every vector in R2. Maybe you can take L as something to get 7, 4. Okay, that is possible. Oops. Yeah. Maybe you can take L as something to give you 7, 4. And basically, you would want x plus y to be 4, and y minus z to be x plus y to be 7, and y minus 3 to be 4. And you can solve that. If I let y be 4 and x be 3, 3 plus 4 is 7, and y is 4, and you must take away 0 to get 4. So x is 3, y is 4, and z is 0. That would work. So maybe it is onto, but it doesn't need to be. Linear transformations don't have to be onto. Now, just for the record, of course this one is onto. Because what would you take L of to get AB? Well, remember, this is supposed to be x plus y, y minus z. If I let y be 0, that is, it's not here. Oh, so then x should be A, y I said is 0, and negative z should be B, so z should be negative B. L of that will give us AB. So it is onto. I didn't mean to get into that big time, but I did. So it's onto. Now, basis T is going to be 1, 2, and negative 1, 1. And the instructions are, well, let's write it. A is 1, 2, and negative 1, 1. And what we want to do is find the matrix A. We want to find the matrix A. So I take L of every vector in the base basis for R3, the given basis. This basis. So I take L of 1, 0, 1. I add the first two entries, x plus y, or x and y are the first two entries, and then I do the second entry minus the third. 0 minus 1 is negative 1. And now I want to write 1, negative 1 as a linear combination of the vectors in T. So I want it to be, I don't know, alpha times 1, 2 plus beta times negative 1, 1. If you can look at this and see the answer immediately, wonderful. If you can't, you have to realize that the top entry, that this is really 1 alpha, I'll just write alpha, plus beta times negative 1, which is negative beta, and the bottom is, and this should equal 1, and the bottom one is 2 alpha, plus 1 beta, plus 1 beta. So let's write it down. Alpha minus beta is 1, and 2 alpha plus beta is that number, negative 1. Now, if I just add these, I get 3 alpha, but the betas cancel, and this equals to 0. So alpha is 0. I didn't see how easy it was. So now we know alpha is 0. So twice alpha is 0. Add beta, you get beta equals negative 1. If you don't see the answer, like I didn't, you can solve it the way I just did. Or, like always, you can solve this system of equations by matrices. 1 alpha minus 1 beta equals 1. 2 alpha plus 1 beta is negative 1. You can solve that. But if you look at that second vector, unlike me, you'll see that it's just negative of the vector we want the sum to be. We want the sum to be 1, negative 1. Wait for the eraser to catch up. Okay. So, what we want is, let's erase this equal sign. We want this sum to be 1, negative 1. Well, if I just multiply the second vector by negative 1, I get 1, negative 1. And I guess I'll add on 0 of the first vector. That is, the coordinates of L of 1, 0, 1 with respect to the basis T is 0, negative 1. Okay. That's L of the first vector in the basis for V. The first vector. Now I take L of the second vector and I do the same thing to it. L of the second vector. I call the first entry X and the second entry Y and the third entry V. And I look at my rule. It says to add X and Y. Add 0 and 1. Okay, 0 plus 1 is 1. And for the second entry, you do Y, take away Z. Okay, 1 minus 1 is 0. And I want this to be a multiple of 1, 2, plus a multiple of negative 1, 1. Okay, now that one seems less obvious. Okay, now we play the alpha plus beta game. The top line is 1 alpha or alpha minus plus minus 1 beta or minus beta is equal to 1. The second line is 2 alpha plus beta. 2 alpha plus beta. Okay, so alpha take away beta is our 1. And 2 alpha plus beta is 0. 2 alpha plus beta is 0. Now, if I add these, the betas cancel. So this time I guess 3 alpha is 1. So alpha is equal to 1/3. Okay? And we know that when we subtract the 2 alpha and beta, we get 1. So 1/3 minus some value gives you 1. Well, you know 1/3 plus 2/3 is 1. 1/3 plus positive 2/3 is 1. Well, we have a rule that says anytime you feel like it, you can change addition to subtraction, so long as you change the sign of the second number. Beta is negative 2/3. Beta is negative 2/3. Because now when you do alpha minus beta, 1/3 minus negative 2/3, you get 1. Okay. So this one, you're really not expected to see in your head. But nonetheless, it's 1/3 and negative 2/3. Okay, let me get rid of my scrap work. Of course, on an exam, you should leave it, but do it on the side. That's why they call it side work. So now I know the coordinates of L of 0, 1, 1 with respect to t. I know the coordinates of this vector with respect to t. L of 0, 1, 1 is a vector. I know it is because it equals the vector 1, 0. But the coordinates with respect to t is 1/3, negative 2/3. 1/3, negative 2/3. Okay, now we find L of the last vector in the basis for v, which is 1, 1, 1, 1, 1. And first we compute x plus y, 1 plus 1, 2, and then we do y minus z, 1 minus 1. So we get 2, 0. Okay, now if this gave me 1, 0, I think if I double it, it'd give me 2, 0. That is, instead of, well, but we have to have 1, 2, and negative 1, 1. But I want to double it. So I won't have 1/3, I'll have 2/3. I won't add that many of those vectors. I'll add twice as many, 4/3. Well, this, and it saves you a lot of time realizing that 2, 0 is a multiple of 1, 0. It was twice it. Basically what I'm doing is 2 times what's in the box here. 2 times 1/3 of 1, 2 plus negative 2/3 of negative 1, 1. So this is one vector plus another vector, and you distribute. Let's see where I can write this. When we had a rule that says C times D times the vector V is the same as CB, that is multiply the two scalars and then multiply by V. And that's kind of what I'm doing now. 2 times the third is 2/3 times the vector 1/2. That's exactly what I have. Plus 2 times negative 2/3, negative 4/3, times the vector negative 1, 1. That's what I have. Okay. So that's the justification why that works. But now I have the coordinates of L of the third vector in the basis S with respect to T. That is L of 1, 1, 1. The coordinates of that with respect to T is 2/3, negative 4/3. So now I have my matrix A. This will be the first column of A, that will be the second column of A, and down here, that will be the third column of A. So let's write it up. So the matrix A is 0, negative 1, 1/3, negative 2/3, 2/3, negative 4/3. That is the matrix A. So what we know is the following. L of x, the coordinates of that with respect to t, is equal to A times the vector x, the coordinates of vector x with respect to s. So how about we let x equal to, I don't know, say 1, 2, 3. Okay? And what is L of 1, 2, 3? Well, x is 1, y is 2, z is 3. So we do x plus y. 1 plus 2 is 3. And then we do y minus z. 2 minus 3 is negative 1. So we have our answer. But we want to verify this using the matrix A. We want to use the matrix A. So what is L of x? So let's look at this line. What is L of x with respect to the basis t? What is, I meant to say, what are the coordinates, what's the coordinate vector of L of x with respect to t? Well, L of x with respect to t. Well, L of x is 3, negative 1. But we want the coordinates of that with respect to t. Or that is the coordinates with respect to t. Now remember, this is the basis for t. So this is equal to 3 times, I get this 3 from there, times the first vector in t, plus negative 1 or just minus 1 times the second vector in T. And 3 times 1 is 3, plus another 1 is 4. 3 times 2 is 6, minus 1 is 5. Okay, now let's see what we have here. Now something's troubling me here. Something is troubling me here. Doesn't look like I did anything wrong either. Sorry about this, folks. Well, alright, let's see. We calculated this. I did it on the bottom, and I got 4, 5. Let us look at the other side of the equality sign. We need to first write x as the coordinates of x with respect to the basis s. And x is 1, 2, 3. I want to write 1, 2, 3 using, or the coordinates of 1, 2, 3 using their basis s. That is so this is going to be this. Well, this implies that 1, 2, 3 is going to be some multiple. So right, I want to write the vector 1, 2, the coordinates of vector 1, 2, 3 with respect to s. So I want 1, 2, 3 to be some multiple of the first vector in s, which is 1, 0, 1, plus some scalar of the second vector in s, 0, 1, 1, plus a multiple of the third vector in s. Now, if you want to solve such a thing, you write down each of these vectors as columns. This is routine 1, 0, 1, 0, 1, 1, 1, 1, 1, and you augment it with what you want, namely 1, 2, 3. Now, this turns out to give us the identity matrix. This turns out to give us the identity matrix with 1, 2, 0. That means C1 is the number 1, C2 is the number 2, and C3 is 0. That is, I get 1, 2, 0. I get 1, 2, 0. Okay? Let me erase my work here. So now I'm ready to finish the computation of the right-hand side. I found L of the coordinates of L of x with respect to t. It happens to be 4, 5. Now I want to multiply my matrix A. Remember, matrix A is right here. Multiply it by the coordinates of x with respect to the basis s. So I take my matrix, 0, negative 1, 1/3, negative 2/3, 2/3, negative 4/3, and I multiply it by the coordinates of x with respect to the basis s. 1, 2, 0. And if you multiply this out, you get 2/3. You get 2/3. And you get negative 7/3. Negative 7/3. Okay. Now, I see where I made my big problem. I'm so sorry. In the bottom here, I want to calculate the coordinates of vector 3, 1 with respect to the basis t. So what this is going to equal is going to come from this. I want 3, negative 1 to be written as a linear combination of the vectors in t. And these are my vectors in t. A multiple of 1, 2 plus another multiple of negative 1, 1. Now this is going to involve me erasing the top and solving this system of equations. Or we claim we have our answer. We computed a times the coordinates of vector x with respect to s, a coordinates of x with respect to s, and here is my answer. And on the left side, we want L of x, the coordinates with respect to t. Well, are these numbers really correct? These answers. 2/3 and negative 7/3. Negative 7/3. Well, 2/3 times 1 is 2/3 plus negative 7/3 times a negative 1 is plus 7/3. This is 9/3 or 3. Got it. And the bottom one is going to be 2/3 times 2, which will be 4/3. And plus negative 7/3 times 1 would be negative 7/3, which is negative 3 over 3, which is negative 1. So it turns out that the coordinates of the vector 3, negative 1 with respect to t is in fact 2/3, negative 7/3. Okay, you could, if you wanted to, actually go and solve this. You can actually go and solve it, but we don't need to. We had to answer. Whatever this is, those two horizontal lines say it's going to be whatever that is. And if you know that, then you know this. If you know one side of the equality sign, you know the other side. Okay, let's try another problem. We'll still work with the same linear transformation. Let L be let L, which is a mapping from R3 to R2, be a linear transformation defined by L of x, y, z is x plus y, y take away z. And you're given two bases, one for R3. S will be 1, 1, 1, 0, 1, 1, and 1, 0, 1. The basis for the basis for R2, which we'll call T, is 1, 2, and negative 1, 1. So we want to find the matrix A. Remember that L of x with respect to t, it doesn't equal to A times x, but it equals to A times the coordinate of x with respect to the basis S. Now, you know how I said how L of x is equal to some A times x? Well, think about it. If t is the natural basis, then L of x, whatever that is, with respect to the basis t, will be L of x. I mean, if L of x is equal to 3, 7, how do you write this using the natural basis for R2, 1, 0, and 0, 1? And their answer is you take 3 and 7. So L of x with respect to the basis t, if it was a natural basis, would just be 3, 7, which is L of x. That is, this is L of x. And same thing on the other side. A is A, but if basis S is a natural basis, then the coordinates of x with respect to S will just be x. So when you use the natural bases for S and t, you just describe the linear transformation as a special matrix A times x. It works like a charm. The thing is, you're not always given a natural basis for S and T for the vector space V and the vector space W. So the problem is to find the matrix A. Well, first you want to find L of each and every vector in the basis for R3, namely these three. What's L of 1, 1, 1? Well, x, y, and z are all 1. Well, then x plus y, 1 plus 1 is 2, and 1 minus 1 is 0. And I want to write this as a linear combination of vectors in T. Some number times 1, 2, plus some number times negative 1, 1. Now realize, no matter what number I put here, I'm going to have 2 times C1, and I want 0. So over here, since I'm multiplying by 1, I need to put negative 2C1. Okay, so basically, I have 1C1 plus 2C1 should equal to 2. That is, 3C1 should be 2. What do you multiply 3 by to get 2? Well, if you have 3, you should divide by 3, that's 1, and then multiply by 2. Or you can just divide both sides by 3, and you'll see that C1 is 2/3. That's slick. C1 is 2/3, and the other scalar is negative 2 times C1, which is negative 4/3. But if you didn't see that, reduce. 1, 2 is this vector, and then you write down that vector, negative 1, 1, and you want to get 2, 0. I'll keep row 1 the same. I'll add row 1 and row 2 for the last one. 0, 3, and 0. I'll divide the second row by 3. 0, 1, 0. Now, amazingly, I'm not getting the same answers. Just call this C2. C1 minus C2. Oh, here it is. They're right in this columns. Sorry about that. 1, 2, negative 1, 1. If I add row 1 and row 2 together, and I put the result in, doesn't matter where I put it, I'll put it in row 2. I get 3, 0, 2. Now I can do back substitution. This line tells me that 3 times C1 is 2, which implies C1 is 2/3. The second line tells me C1 minus C2 is equal to 2. Interchanging these two, I get C1 minus 2 is C2. But C1 is 2/3. So I get 2/3 minus 2 is C2. But I'll write 2 as 6/3. So negative 4/3 is C2. Okay, however you get it, you get it. Okay, you need to become experts in solving linear equations. This is 2/3 times 1, 2, minus 4/3 times negative 1, 1. That implies that I know L of that vector with respect to, I know the coordinates of this vector with respect to t, with respect to the basis t. And it is 2/3, negative 4/3. 2/3, negative 4/3. That's going to be the first column of A. I'm going to stop solving systems of equations at this point. Okay, so now we want to find L of the second vector in S. 0, 1, 1. X is 0, y is 1, z is 0. The x plus y, 0 plus 1 is 1, and y minus z, 1 minus 1 is 0. And I want this to be a multiple of 1, 2, plus another multiple of negative 1, 1. but, there's half of this. There's half of this. Okay? Half of 2, 0 is 1, 0. So what I want is half of 2, 0. This here is 2, 0. I want half of 2, 0. Half times 2 is 1. Half times 0 is 0. So I do get 1, 0. Well, this is 1 half of 2 thirds times 1, 2 minus 4 thirds times negative 1, 1. Half of 2 thirds is 1 third times 1, 2. Half of, well, there's my minus. Half of 4 thirds is 2 thirds of negative 1, 1. So there's my coordinates, including the negative sign. That's my coordinates. I then have to solve the system of equations. I just took half. Okay, so this is equal to 1 third times 1, 2 minus 2 thirds times negative 1, 1, which implies the coordinates with respect to basis t of L of 0, 1, 1 is 1 third, negative 2 thirds. Kind of got that one for free. And please, you too get it for free. Now I want to find L of the last vector. L of 1, 0, 1. X is 1, Y is 0, Z is 1. X plus Y. 1 plus 1 plus 0, 1. Y minus Z. 0 minus 1 is negative 1. So this is not a multiple. 1, negative 1 is not a multiple of this or that. So we need to either hit on it ourselves or or solve a system of equations. So multiple of 1, 2 plus a multiple of negative 1, 1. This may not be a multiple. The 1, negative 1 might not be a multiple of what we got before, but it's a multiple of 1, negative 1. If I multiply this by negative 1, if I multiply this vector by negative 1, I get what I want. That is, let C1 be 0. Okay, so that one's done. So really, all I had to do was rigorously do only one of these. I had to find L of 1, 1, 1. The other two kind of came for free. So L of 1, 0, 1, the coordinates of that with respect to t is 0, negative 1. 0, negative 1. So now I am in a very, very good position to write down the matrix A. Those vectors that remain on the right side of the board, those will be the columns of A. The matrix A will be 2 thirds, negative 4 thirds, 1 third, negative 2 thirds, and 0, negative 1. Let's do another problem. Remember, every linear transformation has a matrix associated with it, such that L of x is A times x. The mapping L from R3 to R2 is a linear transformation defined as follows. It's defined by L of x, y, z is equal to this matrix times x, y, z. Okay. Now, I'm going to give two bases. Basis S contains the vector 1, 1, 0, 0, 1, 1, and 0, 0, 1. That's a basis for R3. And basis T, which will be 1, 2, and 1, 3. This is going to be a basis for R2. And instructions are to find A with respect to basis S and T. Bases S and T. So we find L of each vector in the basis, the given basis for R3. So first we find L of 1, 1, 0. L of 1, 1, 0 is just this matrix times 1, 1, 0, which is 2, 3. And I'll come back to that in a moment. Then we want to, well, maybe I'll need this space. So 2, 3. Now we want to write 2, 3 as a linear combination of the vectors in T. 1, 2, and 1, 3. And whatever we get for C1 and C2, that's going to tell me that L of 1, 1, 0 with respect to T will be C1, C2. Okay, so I need to solve the following matrix. 1, 2, 1, 3, and I want it to be 2, 3. I'll keep the first row the same, and from the second row, I'll take away 2 times the first row. I'll take away 2, 2, 4. And what I get is 0, 1, negative 1. Now, I replace row 1 with row 1 minus row 2. 1 minus 1 is 0. Sorry, is 1. 1 minus 1 is 0. 2 minus negative 1 is 3. The second row did not change. So that's C1 and that's C2. Let me check it. Okay. So now we know C1 and C2. They are, they are 3, negative 1. 3, negative 1. So I have the first column of the matrix A. Get rid of our side work. I promise not to solve systems, but I keep doing it. I want to make sure you guys can solve systems. Okay, now I take L of the second vector in the basis for R3, namely 0, 1, 1. L of 0, 1, 1 is nothing more than this matrix, A times 0, 1, 1. And this time, looks like we get 2, 5. And I want to write 2, 5 as some multiple of 1, 2 plus some multiple of 1, 3. And you should always, always, always spend a second or two to see if you can see it. Well, I know that 2 plus 3 is 5. Oh, what a break. 1 plus 1 is 2. That is, I just take one of these. One of vector 1, 2 plus one of vector 1, 3. Sometimes you can hit on it. So that tells me that the coordinates of L of 0, 1, 1 with respect to the basis t is 1, 1. Now I take L of the last vector in S. L of 0, 0, 1. Well, that's 1, 1, 1, 1, 2, 3 times 0, 1, 0, 0, 1. Which is 1, 3. Now 1, 3, and we should have tried this with the 2, 5. 2, 5 was not a multiple of 2, 3. And 1, 3 is not a multiple of 2, 5 or 2, 3. That means we have to try to work it out. But you know what? It is a multiple of a vector in t. It's going to be 0 times 1, 2 plus 1 times 1, 3. That will give us 1, 3. Okay, this implies that the coordinates of L of 0, 0, 1 with respect to t is the vector 0, 1. And our matrix A is just those vectors we found. 3, negative 1, this vector here, and then 1, 1, 1, 1, and then vector 0, 1. And this matrix is used to find the following. If you want L of x with respect to t, what you do is you take the matrix A and then you multiply it not by x, but by the coordinates of x with respect to s. And that's what we found on the bottom left. We found that matrix that makes this equality symbol correct or valid. You want to make sure it's right. Using an example, you take L of x and you write the coordinates of L of x with respect to t. And then you take x and you find the coordinates of x with respect to s. Then if you multiply that coordinate vector by a, you say, oh, the left and right hand side were in fact equal. Now, I do want to show you a method where you can solve all three of these problems that we just did, and I'll be very clear in a moment which three I mean, with just one augmented matrix, or a triple augmented matrix. Okay, so we found L of 1, 1, 0 is 2, 3, and L of 0, 1, 1, 2, 5, and L of 0, 0, 1 is 1, 3. And then our job was to find these values. Then the next job was to find these values. Okay. So, for example, to find the first set, 3 and negative 1, we wrote down 1, 2 and 1, 3, and we augmented it with what we wanted, 2, 3. Now, if we wanted to use a matrix to find the one and the other one, or to find these two scalars, what we would do is write down 1, 2, 1, 3, and then augment it with 2, 5. And the same thing for the third one. To find the 0 and the 1, we would take 1, 2, 1, 3, and augment it with 1, 3. Now, we keep reducing the 1, 2, 1, 3. Why do it 3? Excuse me. I hope that just came up. Why augment 3 separate matrices? Why not just do 1, 2, 1, 3 and augment it with 2, 3? Augment it again with 2, 5. Augment it again with 1, 3. And I can tell you what you're going to get. You're going to get the identity matrix augmented with 3, negative 1, 1, 1, and then 0, 1. And then you are done. This is your matrix A. Just remove those vertical lines. That's your matrix A. So that's another way of doing it. Probably the cleanest way of doing it, actually. Okay. Letters are another problem. Okay. This time, we'll deal with polynomials. Let L be a linear transformation from the set of polynomials of degree 1 or less into the set of polynomials of degree 2 or less. So let this be a linear transformation defined by L of P of T is P of T times T. So there'll be two parts here. Find the matrix of L with respect to the following bases. Now, if you want to find the matrix of L, it's really helpful to given the natural basis. So, the basis for P1, is T and 1. And the basis for P2, well, you can have up to a quadratic. T squared, T's, and constant. 1T squared, 1T, and 1. We want to find the matrix A. Okay, so first we want to find L of each vector in the basis for P1. We want to find L of T. We want to find L of 1. Well, L of anything, L of any polynomial is that polynomial times T. So it's that any polynomial times T is T squared. And I want to write it as a multiple of these. Well, I hope you realize it's 1T squared plus no T's plus no 1's, which implies that L of T, the coordinate with respect to basis T, is 1, 0, 0. 1, 0, 0. And L of 1, well, L of anything is the anything times T, which is T. Well, T is no T squared. Using those values, no T squares, plus 1T plus 0 1's. 0, 1, 0. This implies that the coordinates of L of 1 with respect to T is 0, 1, 0. So, and those are both natural bases. So, A is 1, 0, 0 for the first column, and the second column is 0, 1, 0. That is the matrix A. I'll leave it on the bottom. Okay, so part B is if P of T is, say, 3 times T minus 2, we want to compute L of P of T directly, so we know the correct answer easily, and also find L of P of T using the matrix A that we just found. Okay, so L of P of T, L of 3T minus 2 is, well, L of anything is T times the anything, which is 3T squared minus 2T. Let me leave that down there. Now, we know that L of P of T, the coordinates of that with respect to T, is equal to A times the coordinates of P of T with respect to the basis S. That is what we know. And up here, I'm going to write the matrix because I need to erase it on the bottom. we know that this statement is true. Now, L of 3t minus 2, I'm just copying this, except P of t, we know. With respect to t, well, I know what L of 3t minus 2 is. It's 3t squared minus 2t. And this with respect to t, well, remember, this here is 3t squared minus 2t plus 0 ones. With respect to the basis t is going to be 3, negative 2, 0. 3, negative 2, 0. In fact, you know what? I don't like what I just did. The reason I don't like it is because I actually calculated L of 3t minus 2. I'm just going to calculate the right-hand side. I'm sorry. I'm going to calculate the right-hand side. I knew something didn't look right. I'm going to calculate A times this. Well, A is this matrix. Now, what is P of t with respect to the coordinates of P of t with respect to S? Well, this is P of t, and I want to know the coordinates with respect to S. Well, isn't it 3 times t minus t times 1? Isn't it just 3, negative 2? That is, isn't it just 3, negative 2? What I'm saying is 3t minus 2 is 3 times t minus 2 times 1, which implies that 3t minus t with respect to S is 3, negative 2. Okay. So 3t minus 2, the coordinates of that with respect to S is 3, negative 2. And when I multiply this out, I get 3, negative 2, 0. I get 3, negative 2, 0. Okay. So what does this tell us? Let's read the beginning and the end. It tells me the following. It tells me that this, the coordinates of L of P of t with respect to t is this. Therefore, L of P of t must be 3 times the vectors in t. The vectors in t were t squared, t, and 1. So we get 3, negative 2, and 0. We get these vectors, which is 3t squared minus 2t plus 0. Just 3t squared minus 2t, which is absolutely correct. Okay, we did it directly, and we got the same answer. And then we did it first we did it directly, then we did it using the matrix A, we got the right answer. Pretty neat. Okay, that worked out well because Well, that worked out well using the natural basis. What if we don't use a natural basis? What if we don't use a natural basis? That is, what if we make this problem harder? So I'm keeping the same definition for L, but I'm going to give two different bases. One for P1, one for P2. Not different from one another, but different from the one that we just worked with. Okay, we'll let S be the same. S just contains T in one. But basis T for P sub 2 is going to be different. It's going to be T squared, T minus 1, T plus 1. And it's the same instructions. Find the matrix A. Okay? So I need to find L of T. I need to find L of 1. So it's T times T, T squared, and it's T times 1, which is T. I want to write this using the basis T. Well, T squared is just 1T squared and nothing else. That is plus 0 times T minus 1 plus 0 times T plus 1. Well, this tells me that the coordinates of L of T with respect to T is 1, 0, 0. 1, 0, 0. And having seen I didn't have enough space, let me move this over a little bit. Now I find L of the second vector in the basis for P1. L of 1 is T times 1, which is T. Now, I know for sure that it's no T squares, but how many T minus 1s plus how many T plus 1s? Now, you really need to start to think. A multiple of T minus 1 plus a multiple of T plus 1. And we want to get just 1T. That is, we want the constant to be 0. Here we have negative C1, and here we have plus C2. If this number was C1 as well, we'll get 0. Negative C1 plus C1. It's done. We get the 0. But we want to get T. We want to get 1T. Well, we have C1T plus C1T. I don't care what the things look like. If you add it together twice, you get 2 times it. And you want this to be 1T, excuse me. Well, 2 times a half is 1 times T. C's are a half. Each of these values, C's, are a half. They are each a half. They're each a half. If you didn't see that, not a big deal. But please, you have to see that it's 0 times T squared. That you had to see. Okay, you need to write out a system of equations. Cool. And you have to do what you have to do. So you have C1 times T minus 1 plus C2 times T plus 1 should be 1T. So you have C1T plus C2T. You have C1 plus C2T plus negative C1 plus C2. And this should be 1t plus 0. That is, this should be 1, and this should be 0. Okay? So C1 plus C2 is 1, and C1, negative C1 plus C2 is 0. If you add these, that cancels out. You get 2 C2s is 1, so C2 is a half. What plus a half gives you 1? A half. C1 and C2 are both a half. They're both a half. I did it the thinking way, like always, and I did it the mechanical way. Of course, I'm going to see more things than you. Okay, so this implies that the coordinates with respect to t of L of 1 is 0, 1 half, 1 half. Make sure you include the signs. 0, 1 half, 1 half. So matrix A is nothing more than 1, 0, 0. Oops. 1, 0, 0. 0, 1 half, 1 half. I just wrote down those two matrices as the columns of A. Now, let us do another problem. Suppose P of t is, once again, 3t minus 2. And we want to compute P of t using the definition directly. And the next part, use it with the matrix. So L of P of t, better known as L of 3t minus 2. Well, L of any matrix is, L of any polynomial is t times that polynomial, which happens to be 3t squared minus 3t. Now, we know that L of P of t with respect to the basis t is matrix A times P of t. Actually, A times the coordinates of P of t with respect to S. Now, we know what A is. It's 1, 0, 0, 0, 1 half, 1 half. What we don't know yet is what P of t is, the coordinates of P of t with respect to S. P of t is 3t minus 2. Okay. 3t minus 2 with respect to S. Well, first, before we can find out what that is, we need to write 3t minus 2 as a linear combination of the vectors or polynomials in S. And S is t and 1. So it's a multiple of t plus a multiple of 1. The answer is 3 and negative 2. That is, the coordinates of 3t minus 2 with respect to S is 3 minus 2. Because S is the natural basis. So we just got 3 negative 2. Okay? 3, negative 2. And when you multiply these matrices, you get 3, negative 1, negative 1. Okay. So we did not learn what L of P of T is yet, or L of 3T minus 2. We didn't find that yet, but we're almost there. I'm just copying down that this equals 3, negative 1, negative 1. L of, I'll write down what P of T is. The coordinates of this is equal to 3, negative 1, negative 1. Well then, what's this? This information tells me that L of 3t minus t is, now I write down the vectors in t. T squared, t minus 1, and t plus 1. And these are my scalars. 3, negative 1, negative 1. Well, I'm going to get 3t squared. And I take away t, and then I take away another t. I take away 2 t's. Don't forget to add 1, and then take away 1. That is, add nothing. But this is correct. This was L of 3t minus 2. And after all, if you multiply this by t, like you're supposed to, you get this. Okay, so what you need to do is to practice to get it down cold. If you know this, what's this? What's L of 3t minus 2? And the answer is you take the vectors in basis t and you multiply them one by those scalars. That was the first vector in t, excuse me. This here was the first vector in t, 3t minus 1 was the second vector, t plus 1 was the third vector, and I multiply them by 3, negative 1, negative 1. The coordinate vectors. And I got the right answer. I got 3t squared minus 2t. This completes the section entitled the matrix of a linear transformation, and in fact, it completes the linear algebra video. I hope the video was helpful, and I wish you great success in your course, I guess your upcoming final. Thank you. Good luck.